Good morning, my name is Matthias Fresacher, and today I'm going to be talking to you about congruence lattices of finite twisted Brauer monoids. To begin with, I'd like to give you a quick overview of what I will be covering today. So obviously, I'm going to be talking about diagram monoids, and I'm going to provide some motivation why they, and specifically the Brauer monoid, are of importance. And I'm going to generalize this to be in a twisted setting. I'm also going to talk about congruences, explaining what exactly are they, give some examples, and explain why they are important. That will allow me to state the theorem I was able to prove, give an outline of that proof, as well as some possible future directions for this work. The key takeaway I'd like you to have from today's talk is that the technical maths results I'll be presenting as being done by pictures. And this is going to be done on two levels, one at the diagram level and two at the congruence level. So let's get into it with the Brauer monoid and an example use case. And this comes from statistical thermodynamics, where the interactions between atoms are modeled by matrices. And these matrices are actually elements of an algebra, specifically a twisted semigroup algebra. And that semigroup is actually the Brauer monoid. And this whole construction is usually called a Brauer algebra. So we can see if we understand more about the Brauer monoid, we gain insights into statistical thermodynamics in this example. And this is not the only example. There's others in fields such as biology, representation theory, invariant theory, and knot theory, just to name a few. So what exactly is a monoid? Well, it's a set together with a multiplication operation, and that operation has to be associative, and there has to be an identity element. For the Brauer monoid, Bn, its elements are the Brauer diagrams, and these are usually denoted by two rows of vertices with them numbered from left to right, and the bottom row being dashed numbers. And within that, we have some edges. So the Brauer monoid has the condition that every vertex must be connected to exactly one other vertex. So we have a pairing up of vertices, if you will. We can talk about the degree of an entire monoid, and this counts how many vertices there are. So this diagram belongs to a Brauer monoid of degree 5. We can also talk about the rank of a specific diagram, and this counts the number of transversal edges. So transversal meaning it connects the top and the bottom row. So here we have 1, 2, 3. So this diagram has got rank 3. For the Brauer monoid, it holds that the rank and the degree always share the same parity. Concatenation, well, that's the multiplication operation for this monoid. And for those of you that are visual-based learners, this is an animation of that procedure in action. For everybody else, I'm going to make use of this intermediary step to show how we end up at the concatenated diagram. So let's go through the steps of calculating alpha times beta in detail. So first, we need to position the two diagrams, one directly on top of the other, and then we draw in these red in-between vertical edges. We then remove the two inner rows of vertices, and we remove any loops that are created. So a loop is any collection of edges that are not connected to the top or the bottom row. So we have an example here, and we have a second example here. And we've removed these loops because they don't affect the final concatenated diagram. This is going to be different in the twisted setting, so just keep that in mind. And then we tidy up what we have. So we're going to squish our two rows back to normal size, and we're going to draw clean edges where they exist. We can see that this operation is in fact associative, and it has an identity diagram, specifically just all vertical edges. But the operation is not necessarily commutative, nor does it necessarily have inverses. Now let's talk about the twisted Brauer monoid. So this is where loops matter. So recall a loop is any time we had some edges that are not connected to the top or the bottom row of vertices in our concatenation process. So roughly speaking, the zero twisted Brauer monoid is your standard Brauer monoid with the addition of a zero element. And it's really important to note here that that zero has got nothing to do with this zero. In terms of multiplication, well, trivially anything multiplied by 0 is going to be 0. And if there are no loops present, then our concatenation is just going to be as we had on the previous slide. But if there are any loops present, so as is the case in this example, then our product is by definition equal to 0. So we can see that these two diagrams in the twisted setting have a different product than what they did in the non-twisted setting. For those of you familiar with it, this is in fact a Brauer algebra with a twisting coefficient equaling to 0. Now moving on to congruences. What are they? Well, they're an equivalence relation, usually denoted by sigma, on our set of diagrams. But it must be compatible with concatenation. And by that, I mean if I have a diagram alpha and a beta, if they're congruent, if I multiply it on the right by any other diagram, say a gamma, I must still be congruent. And I want exactly the same property to hold for on the left. Some easy examples include the universal congruence, where everything is congruent to everything else, and likewise the trivial congruence, where everything is only congruent to itself. In between these two extremes, we have a lattice with subset inclusion. So you can picture this as having the trivial congruence at the bottom, the universal congruence at the top, and all sorts of different congruences in between. If I were to take an arbitrary monoid, this congruence lattice would be horrendously complicated. But it's a pretty remarkable fact that for diagram monoids, these lattices are very simple and can be as simple as just a chain. We will also need the notion of a principal congruence. And this is where I take an alpha and a beta, I define them to be congruent, and I look at what's the smallest congruence that contains that pair. Why are congruences important? Well, because they govern quotients in exactly the same way that ideals are important for rings and normal subgroups are important for groups. So if you recall our motivating example, that for our algebra, well actually it's not usually the whole algebra that is appearing in the examples. It's actually a quotient of it. And hence we not only need to understand the Brauer monoid, we also need to understand congruences because they tell us about the quotients. Before I continue, I need to take a quick detour into some semigroup theory, specifically Green's relations, which are some equivalence classes on our set of diagrams. First up, we have the R relation, and two diagrams are related if their top rows are the same. And by that, I mean if a vertex is part of a transversal edge, in the other diagram, that same vertex must also be part of a transversal edge. And likewise, if a vertex belongs to a non-transversal, then in the other diagram, it must also be non-transversal. This is an important not R example, and even though all four vertices here are non-transversal, for non-transversals, the actual edge must be the same across both diagrams, which is clearly not the case here. In an analogous way, we have the L relation, and here two diagrams are L related if they have the same bottom row. We can take the intersection of these two, that gives us the H relation, and two diagrams are H related if both their top and their bottom row is the same. And the H classes are actually in bijection with the symmetric group of that rank. And we can see that in this example here. We're dealing with rank 2, and we have the two elements of the symmetric 2 group appearing. This bijection is going to be important for later on, so keep it in mind. Instead of the intersection, I can take the union, the join, and that gives us the D relation. So two diagrams are D related if they have the same rank. We'll also need the ideals for this monoid, and these are the sets of all diagrams with a given rank or less. And finally, we'll need a hat map. This is defined for even degree, and essentially all it does, it annihilates any transversal edges in the obvious way that you would expect. So now let's go through the congruences. So to explain this, I'm going to make use of an egg box diagram, and this is for the zero-twisted Brauer monoid of degree 6. And the asterisk is here because this is an entirely made-up example. So this egg box diagram, you can think of it as being full of little dots, and each dot represents a single element in the monoid. So for example, at the bottom, we would have the 0 element, and all the dots, hence elements in here, are going to be of rank 0, so they belong to the D0 class. Then in here, we have all the diagrams of rank 2, that's D2, and then rank 4, and obviously rank 6 at the top. If we have two dots and hence diagrams in the same row, then we know these diagrams are related. And likewise, if they're within the same column, then they are L related. Hence, we know if they're actually within the same box, they are H related. So the first congruence we're going to look at is the Rees congruence, where everything is trivial and we collapse the entire Keith ideal. So visually, if we're say looking at the second Rees congruence, we collapse the second ideal, that's everything of rank 2 or less, so that's everything in red here. This becomes a single point or a single representative. Then we have some group-based congruences, where we take the Rees congruence of the rank underneath, and in the current rank, if we are H related, recall that gives us a bijection into the groups. And if we have some group action, which I'm not going to explain or define, then we're also congruent. So if we look at an example of, say, the alternating 4 group, we would have the Rees 2 congruence, so everything of rank 2 or less being identified. And then in rank 4, if we're H related, so we're in one of these boxes, well, our group action, the alternating 4 group, it has got odd and even elements, so you might either be in the blue or in the yellow section. And this gets repeated across each of the H classes in D4, but it's important to note that the equivalences within a H class are different, hence why they have slightly different shaded colors. A different example is the symmetric 4 group, where we again have the Rees 2 congruence, so the second ideal being collapsed, but this time our group action is actually much more encompassing. In fact, anything that is H related is going to be symmetric 4 group related, so our H classes get collapsed entirely just to a single point or representative. Next, we have some lambda congruences, starting with lambda up, where we take R as 2 as a starting point, and if we are R related and have the same hat, we can also be congruent. So recall R as 2, everything of rank 0 or less being collapsed, and H classes in rank 2 being collapsed. And then if we are R related, so within the same row, if our hats are the same, we're also congruent. So potentially some of these H classes are going to get identified across a row as long as their hat is the same. And this gets repeated for each of the different rows. In an analogous way, we have lambda down, and this is where we swap out the R relation for the L relation. So this means our H classes now potentially get identified across a column instead of the row as was the case previously. And the final lambda congruence is just straight lambda, where we drop this R or L condition and just require the hats to be the same. And this is actually the join of lambda up and lambda down. So visually, this means our H classes can potentially get identified across a row or column as long as their hat is the same. And then we have some mu-based congruences. So mu as 2, where everything is trivial, except in rank 2, where we need to be H-related. So that means we collapse our H classes in D2, everything else stays trivial. And our final congruence, the most complicated one we're going to encounter, is mu Klein 4. And this is where we take lambda as a starting point, and in rank 4, if we're H-related and Klein 4 related, then we're also congruent. So recall lambda, everything in rank 0 being identified, H classes in D2 being collapsed and potentially identified across a row or column as long as our hat is the same. And then in D4, within a H class, if we have the Klein 4 action, so that gives us 6 equivalence classes. So I've only drawn 2 because of color reasons in here, but we've got 6 different equivalence classes and they get repeated across each of the H classes. That now allows me to state the theorem I was able to prove this year, and this is for the zero-twisted Brauer monoid, and it says that the congruences I just went through with you on the previous slide are in fact all of the congruences for this monoid. And the congruence lattice is in the odd degree, a simple chain where we work our way through the Rees congruences with the group-based congruences interleaved as you would expect. And in the even degree, we have this same chain, particularly in the tail, but at the bottom we have 3 diamonds. So this is where we find the lambda congruences and our 2 mu congruences. So let's have a look at these diamonds in a little bit more detail, starting with the trivial and R0 congruences. So if I have a diagram, and if I have exactly the same diagram, then they're going to be trivially congruent. Now if we look at these 2 diagrams, they're both of rank 0, so they are a part of Rees 0, which identifies anything of rank 0 or less, but because these are different diagrams, they cannot be a part of the trivial congruence, and hence we have a strict subset here. Now continuing, having a look at R0 and mu S2. So let's move R0 across and bring in two new diagrams. These diagrams are of rank 2 and they are H related, so both their top and bottom rows are the same, and hence they are a part of mu S2. But because they are of rank 2 and reach 0 only identifies up to rank 0, mu S2 cannot be a part of R0. And similarly, these two diagrams are of rank 0, but mu S2 only identifies diagrams of exactly rank 2, so R0 can also not be a part of mu S2. We have two congruences that are incomparable. And finally, let's have a look at RS2 and lambda down. So recall R0 is a subset of RS2, so these two diagrams are also going to be RS2 congruent. And these diagrams are lambda down congruent because they have the same hat and they are L related. But they are not R related and hence cannot be a part of RS2. We have a strict subset. And obviously you can repeat this analysis for the other pairs in this lattice. From this result, it's not too much more work to show that the monoid is also congruence permutable. In terms of a proof, well, the first step is to prove that all the congruences that I claim are congruences are in fact congruences. And then I need to consider every possible pair alpha and beta and look at the principal congruence that pair generates and show that it is contained in my list of congruences. I then need to show my list of congruences is closed under joins, and once I've done that, I satisfy the hypothesis of a lemma by East, Mitchell, Ruškuc, and Topi, and this lemma says that my list of congruences is in fact the entire list of congruences for this monoid. To give you a bit of a better sense of checking all of the different alphas and betas, this is the decision tree I used, and for each leaf in red is the corresponding congruence. So first up, I check, are the two diagrams the same or are they different? Is one the 0 diagram or are both non-zero? Do they have different ranks or do they have the same rank? Are they H-related or not? I then look at some low ranks to pick up on the diamonds in the even degree setting. And over here, I check if their hats are different, because if they have the same hat, I need to look at exactly why are they not H-related. And over here, I need to take care of the Klein for action. Each of these leaves represents a substantial lemma or potentially a proposition, which in turn has a number of subcases that needed to be considered. That brings me to the end of my talk, where I introduced you to some diagram monoids, specifically the twisted Brauer monoids, and we looked at some congruences, specifically the congruence lattices of the 0 twisted Brauer monoid. What would be the next steps for this work? Well, I looked at the 0 twisted Brauer monoid. There's a more general construction for arbitrary D, and it would make sense to analyze this situation. But to give you a sense of the added complexity in doing so, this is the congruence lattice when D is just equal to 2. It's a significant step up. There is an even harder version, and this is an infinite twisted version, where in hand-wavy terms, D is equal to infinity. It would also be nice to consider this setting. That would conclude the analysis of the Brauer monoid and its various types, and it would make sense to repeat this for other monoids, such as the Tempeli-Lieb, which is a submonoid of the Brauer monoid. Throughout this work, I've also developed a LaTeX package BM Draw, and this draws the graphical representations of the diagrams, and this is now available on CTAN, and I encourage you to make use of that and explore its capabilities. Hopefully by now you have learned some rather technical maths with the help of diagrams.